Okay, in the last video we introduced the idea of the carbonyl compounds undergoing nucleophilic addition reactions, where we took a nucleophile, something with a lone pair of electrons, and that was able to donate the pair of electrons and form a bond with the delta positive carbon atom, and as that occurred, the pi bond in the carbon-oxygen double bond would break. We're going to look in more detail at this mechanism. This is a really important mechanism that regularly features on the Year 13 exam papers. There are two specific examples of nucleophilic addition that you have to learn. They both follow roughly the same, clearly the same mechanism, but there are some subtle differences. The first of these is when we react aldehydes or ketones with this crazy compound, NaBH4. Now, NaBH4 is something that you need to learn. It is effectively a source of this somewhat unusual ion, the H- ion. The H- ion is able to behave as a nucleophile because it's got a lone pair of electrons. The second mechanism, also nucleophilic addition, is when we react either our aldehyde or ketone with hydrogen cyanide, sounds exciting, in the presence of cyanide ions. One pair of electrons can behave as a nucleophile. Now the cyanide ions are going to be added either in the form of sodium cyanide or more likely potassium cyanide. So the reagents would be hydrogen cyanide in the presence of sodium cyanide or potassium cyanide. We'll talk more about that in a moment. Let's start with the first one of these, NaBH4. Now this is relatively straightforward. I'm going to take this particular aldehyde. 2 carbons, so this is ethanal. No number because the aldehyde group is always on carbon number 1. NaBH4 is a source of H-. So this is what we're going to put into the mechanism. We don't need to worry about writing in NaBH4. You need to know that, that's the reagent, but we're going to have H-. We need to add on our bond polarities. That's really important. So the first thing that happens is curly arrow from the lone pair of electrons, because remember, a curly arrow shows the movement of a pair of electrons. That was once worth 2 marks on an exam script, back in about 2005, something like that. Curly arrow, movement of a pair of electrons. Now as that happens, we've already said, pi bond breaks. So if we were to draw what happens as a consequence of that, clearly that hydrogen has now formed a bond to this carbon, and this oxygen now has a pair of electrons on it and a minus sign. Notice how the charge, overall, this adds up to minus. The charge is preserved. This adds up to minus. Charge is preserved through a mechanism. Now it doesn't just stop there. We've got this lone pair of electrons on the oxygen atom. We've got a choice of what we do next. If you want to keep your life simple, there's one option. If you want to make it slightly more complicated, there's another. I'm going to show you both of these. So, if we take what we've just formed, We can either react this with an H+, that's the most straightforward option, or we can react this with some water. If you choose to react it with water, you've made your life slightly more complicated because there are more curly arrows to remember. But ultimately, what is it that you make? Well, in both cases, you are describing the same mechanism. You have made an alcohol. Well, why on earth would you want to do that? What's the point in taking something like an aldehyde or a ketone and turning it back into an alcohol when you've already learned how to turn an alcohol into an aldehyde or a ketone? Organic synthesis is about being versatile. It's about being able to take any functional group and turn it into something else. And sometimes it's important to be able to take an aldehyde or a ketone and carefully change that functional group back into an alcohol. And you may need to do that for a whole variety of reasons. The exam board think this is really important, and I'd agree with them. So you've got a simple method and a more complex method. If you're going for the more complex method, it's really important that you do it very carefully and show all of these key features of polarities and all of the curly arrows. Look carefully where all of the curly arrows begin. They always show the movement of a pair of electrons. So the curly arrow starts where the electrons are at the beginning, and they show where it is moved, where that pair of electrons is moving to. Okay, so the second one of these examples of nucleophilic addition is when we react our carbonyl compound. I'll start with ethanol again, and we're going to react it with hydrogen cyanide in the presence of cyanide ions. So that cyanide ion, as we've said, will come from either sodium cyanide or potassium cyanide. First of all, draw in what is important. We've got a polar bond, delta negative oxygen, delta positive carbon. The bond polarity arises because the oxygen is more electronegative than the carbon. We now react our aldehyde or a ketone with our nucleophile. And when we're doing the hydrogen cyanide in the cyanide ions, it is the cyanide ion which acts as the nucleophile. Remember, a nucleophile is something which has a lone pair of electrons and is able to donate that lone pair of electrons. A nucleophile is a lone pair donor. A bond's formed between that lone pair of electrons and the delta positive carbon atom. And as that occurs, the pi bond breaks. And the pair of electrons from the pi bond move onto the oxygen atom. So let's see what we've formed. The structure of the intermediate is this. What I'm interested in, I'll make that a bit clearer, is I've formed a bond between my carbon and my carbon. Oh, that's interesting. So I've got my what's called a nitrile group, okay? Cyanide ion makes a nitrile group. And then we've got what we've seen before in this mechanism. Now, one of the reasons that you would do this, because let's face it, it's pretty hazardous messing around with hydrogen cyanide. You're going to want to do this for a reason. And one reason is to increase the length of the carbon chain. This carbon chain had two carbon atoms in, and this one has got 3. It's quite difficult to do that in organic synthesis, and this is a really neat method of achieving that objective, making the carbon chain longer by 1 carbon atom. Okay, let's get back to the mechanism. What happens next? Well, this is where the hydrogen cyanide comes in. Very similar to the more complex version of what we did when we reacted our aldehyde or ketone with NABH4 and the H- ion. The last part of the mechanism, look, has a similarity to this one. It's just that obviously we're using a different substance. Now what that results in, clearly again, is this. Formation of an alcohol group. We also, interestingly, reform the cyanide ion. So that cyanide ion can go on and react with more of the aldehyde or ketone, whichever we started with, but we've now made a compound, which we've already said, we've increased the length of the carbon chain, and we've also introduced an alcohol group. I've already mentioned the idea that this is called a nitrile and an alcohol. When we come to name them, we call these hydroxynitriles. This is a really interesting molecule because I can see I've got a carbon atom surrounded by four different functional groups, four different groups. There'll be more about that in a later topic. This basically is the mechanism of nucleophilic addition. It's the second example using hydrogen cyanide in the presence of cyanide ions. Those cyanide ions come from either sodium cyanide or potassium cyanide.